Let's work through an example tree processing problem together. In this example, I'm going to focus in great detail on a problem-solving process. You've solved a lot of problems in this course already, and so hopefully you've developed your own process. But now is a great time to really think about what the process is that you go through when you read a problem and you don't know how to solve it right away. Because let's be honest, for most problems, it's not obvious how to solve them right away. That's true on exams. That's also true when you're building software for independent projects. And so, you need some method to get yourself unstuck after reading the problem description and work your way incrementally toward a solution. Now, I don't expect everybody's problem-solving process to be the same, so I'm not going to be very prescriptive about how you go about it. But I do want to talk through some possible elements in an effective process for problem solving. First, we need a problem. Implement bigs, which takes a tree instance T containing integer labels. It returns the number of nodes in T whose labels are larger than any labels of their ancestor nodes. And here's an example. I would recommend that you follow the same process, whether you have a template giving you a hint about the structure of a solution, or whether you're writing the program from scratch. That you don't start writing code right away, or even think about what code might be there already. But instead, think about the problem you're trying to solve. Step 1. Understand the question. The first sentence looks pretty straightforward, but the second one, it returns the number of nodes in T whose labels are larger than any labels of their ancestor nodes. That's the heart of the question, and it's less straightforward. It's very abstract to talk about labels and ancestor nodes without focusing on a concrete example. Unfortunately, one's presented to us. So after reading the problem carefully, perhaps making notes that T is a tree, that bigs should return a number, it's time to work through an example and study it for a while before ever trying to write code. Now here we have a tree and a drawing of that tree. If this drawing were not here, you should draw it yourself, whether you're trying to solve an exam problem or implement something on your own. A diagram is almost always helpful. And now we need to figure out an example of this notion of a node that has a label that's larger than the labels of the ancestor nodes. So let's pick a node. Every one of these numbers is a location in the tree, and a node is just a location in the tree. Now each location in the tree is the root of a subtree. So here's one, 5. Is a node, what are its ancestors? Well, that's its parent, or its parent's parent, or its parent's parent's parent. Probably on an exam I would define that for you. And then we can check this property. Is it the case that 5 is larger than 4 and 1? Yes. So that's actually one of the nodes in this tree that we're looking for. Knowing that the answer is 4 is really not that helpful. We need to figure out which 4 nodes have this property. So let's go through and check them all. How about we start at the top? 1. Is it larger than all of its ancestors? Well, it doesn't have any ancestors. So let's say yes. And we'll check later and make sure that matches with the example that's provided. 4 is larger than its only ancestor 1. So that counts 2. But this 4 is not larger than 4. And so it's not one of the nodes whose label is larger than the ancestor labels. Okay, how about 3? 3 is larger than 1. Notice that 3 has nothing to do with 4 or 5 because those are not ancestors. That observation might help me write the function when I go about that in a moment. 0 is not larger than 3, so it doesn't count. 2 is larger than 0, but it's not larger than 3, which is an ancestor, and so it doesn't count either. So this example helped me find something to be careful about. I can't just look at the parent, I have to look at all of the parents' parents and parents' parents' parents in order to figure out whether it's one of the nodes I'm trying to count. Okay, so we got the number 4, and that means that I correctly classified the top node. And so I've discovered something about the problem. The root label is always larger than all of its ancestors because it doesn't have any ancestors to be smaller than. Now, before trying to just write out the implementation, it's worth thinking about what I expect to appear somewhere within the implementation. I might expect typical tree processing patterns. Like maybe this is one of those problems where you see if t is a leaf, you do one thing. Otherwise, you aggregate recursive calls applied to each of the branches. Well, if I knew how many nodes with this property appeared in all of the branches, then I could just worry about the root node and I'd be done. So this seems pretty good. But I think the problem with this structure is that if I've made a recursive call and then another recursive call and I've reached a leaf, it's hard to tell whether that leaf is a node whose label is larger than the ancestor nodes. Because at this point, I only know about the leaf itself, and some of these leaves have the property and some of them don't. So I can't figure out a way to make this typical structure fit. Instead, I'll have to try something else. If you think about an option for implementing and it doesn't work out, I don't think that's a problem as long as you work through that option quickly. Notice what's wrong with it and then move on. So now we want to enumerate what the solution should have. It should have some way of incrementing the total count. That's what I did when I worked through an example. I looked at each node and either added it in as one of the elements that I'm counting or not. I also need to check for a particular node whether it has this property. And so I'm going to need a line something like, if some node's label is greater than the max of its ancestor labels, then it's larger than all of its ancestor nodes. And so I would need some way to track the list of ancestor labels that I've seen so far. Or maybe there's a more efficient way. Maybe I'll just track the largest ancestor I've seen so far. Then I can check and see if the node's label is greater than the max ancestors. Now, if I were solving this problem, I would recognize that as a useful hook. And I would try to figure out whether I can build the rest of the implementation around this idea of tracking the largest ancestor so far, comparing that with the node's label, and somehow incrementing the total count whenever that occurs. Now it's time to read the template. Here it is. I do recommend pausing the video and trying to solve it yourself, and then I'll walk through one solution process in 3, 2, 1. So the first thing I would look for is how are we going to track the largest ancestor? Here we see a helper function, f, defined as a 2-argument function. So that could tell me which node I'm looking at, and also what's the maximum label of any ancestor for that node. And that seems to get around the problem I noticed earlier, which is that when I'm looking at a leaf, I don't know whether it's one of the leaves that I want to count or not, because I didn't know what the maximum ancestor value was. But now I have a 2-argument function, so I can keep track of that second piece of critical information. Now this is a common pattern in recursive functions. We're writing a recursive function that doesn't track all the information we need, so we define another function. Biggs is going to call f, and then f is going to call f. F will eventually return exactly what Biggs was meant to return, and then Biggs can just return whatever f gave it. I had made a note earlier that I was going to compare a node's label to the maximum ancestors. Now, one thing that's artificial about taking an exam is that sometimes I force you to use particular names that are different than what you might choose. So instead of writing node.label greater than max ancestors, you should write a.label is greater than x. As soon as I write down a.label greater than x, I would write a note to myself to remember what a and x represent. This is a node in T, so some tree, and x is an integer representing the maximum label of any ancestor seen so far. If these abstract descriptions don't work for you, then write down an example. A is this subtree, 4, 4, 5, and max ancestor is 1, the largest ancestor of this subtree. All right, now we need to implement the pattern where Biggs calls f, and then f computes the answer. And that means Biggs is going to call f on the whole tree so that the entire thing gets analyzed to find all the nodes we're looking for. But I do need to call f with 2 arguments. So I need some initial value for the largest ancestor so far. I might not even fill that in right away. I just know that I need it at some point, and so let's worry about it later. But having the right formatting means that we're on our way to writing correct code. All right, what other notes did I make along the way? I needed to somehow increment the total count. Biggs returns the total count, so f returns the total count. So the total count is 1 plus, and here I need to write down an expression that tells me the total number of nodes in A aside from the root node that have the property I'm looking for. And here's where we apply that classic pattern of recursively calling f on each of the branches and then aggregating the results. And since I'm counting, I'll aggregate with a sum. So sum of f applied to each b for the b and a dot branches is a common pattern. Why a instead of t? Well, we want to walk through the tree. Biggs calls f on the whole tree, which calls f on its branches, which calls f on its branches, etc. And that way we can analyze the whole tree. Now, one challenge with writing recursive functions is to figure out what arguments to pass into the recursive call. But since I've made notes, there's hope. I know that I need to call f with some value that represents the maximum ancestor label I've seen so far. X was the maximum ancestor label before I looked at A, and A's label was even bigger. So that means A's label is the largest ancestor label I've seen so far because it's bigger than whatever was the largest before looking at A. So by understanding what these names X and A represent, I'm able to figure out what argument to pass in when I analyze the next branch. And what if I haven't found a node whose labels are larger than all the other labels of the ancestor nodes? Well, then I still have to look in the branches. Maybe there will be another node there. Imagine that down here somewhere there was a 12. Well, it would certainly be larger than the 1 and the 3 and the 0 and the 2 that were above it. And so you have to keep looking, even if the node you're looking at isn't one that has the property you want. And so again, we follow this pattern of summing over recursive calls. But this time we have to think about what's the maximum ancestor value. A.label is not greater than x, and x was the max ancestor before, so x is still the max ancestor now. We've filled in almost the whole implementation, except for that one fact that I noted very early on. The root label is always larger than its ancestors. So we want it to be the case that when f is called on the root of the whole tree, this expression is always true. Now I could pass in a third argument telling me whether it's the root or not, or I could just make it work. For example, I could make it work by passing in some maximal value that's not actually the maximal value, but instead is just something that's less than t.label. That's one way to solve this problem, that the root is different than everything else because we haven't seen any ancestors so far. Okay, we're done. And what are the useful tips? Work through an example. Draw it out. If you are ever at risk of forgetting what A and X mean, then label them, either with a description or with an explicit example of what values it might take. When you make recursive calls, make sure you're making recursive calls with the right kind of value, and with values that make sense based on what these names actually mean. And finally, check your work. Here, I would go through every node and try to trace through my code in order to make sure that I get the number 4 at the end. So, the first thing I would do is call f on 0, that's t.label minus 1. And since 1 is greater than 0, I would return 1 plus something else. And what is this something else? Well, I would call f on this node, this subtree, with a label of 4, and I would pass in a.label, the number 1, as the max ancestor. Okay, 4 is greater than 1, and then I'll call f on this node and 4, but that doesn't add 1. And I would call f on this node and 4, and that would add 1. Now it's worth thinking about what happens with this sum when you're at a leaf. Well, there are no branches in a leaf, and so the sum will come out 0. Okay, so I've got 1 so far, and 0 here. And that means I'm adding 1 to the sum of 0 and 1, so I've counted up 2. And then I make a recursive call on the other branch of the original tree T. In this case, I call f with the max ancestor as 1, and that will increase it by 1 again. Here we have the max ancestor of 3. 0 is not bigger than 3. I still make the recursive call, but 2 is not bigger than 3, and so I count up 4 in total. And now you see the whole reason why I emphasize what would Python display in environment diagrams, is because you do have to be able to go through and trace what your program would do in order to check your work. And you might think that with a computer, you don't have to do this because the computer will do it for you. But figuring out why a function is not doing what it's supposed to be doing almost always involves you manually tracing through what it's doing by understanding exactly how expressions and statements are evaluated and executed in a programming language. And checking your work is a critical step in solving problems.